Can you guys hear me okay? Excellent. All right, well, thank you very much to the organizers for the invitation to speak today. As it was said, I've been working on off-road robotics for over 20 years, everything from underground mining to planetary exploration to military vehicles, marine vehicles, trains, if you count that off-road, all kinds of different things. And today I wanted to maybe do something a little different. So the theme of the workshop is resilient off-road driving. So I wanted to think about a different aspect of resilience, which is trying to make sure that our perception is actually resilient to things like dust and rain and bad weather and fog and all of that kind of stuff. So I want to try to make the case to maybe think about radar, which is something that I think is a little undersubscribed in robotics. And maybe I'll convince you that it's something that's worth looking at by the end of the talk. So these are some of the robots that we've been using with radar. We started on the road, and I will talk a little bit about what we've done on the road, and then we've moved to off-road and trying to think about how we can use radar for driving around in forests and things like that. So before we get into radar, I just want to say I actually do really like cameras and LiDARs and other kinds of sensors. So this is some work we did almost 10 years ago where we're driving around off-road using cameras only. It's only using cameras. There's no GPS. We're building maps in a demonstration phase and then repeating routes just based on stereo cameras. And, this was before the era of deep learning, so we were still robust to lighting by sort of building maps and then layering new layers every time we drove on top of that map so that we had many, many experiences and we could sort of span the ways that the world looked. So cameras are great, but they have a lot of challenges. And already with lighting, you're getting into very complicated algorithms just to handle them, just to handle that. I also like working with LiDAR. This is some recent work where we were trying to do similar route following based on LiDAR. This is actually for a lunar rover mission. And you can see this robot it's quite a big robot. It's about as tall as this room when it's got its payload on it, and it's able to drive around using LiDAR. And in a lot of situations, that's going to be robust. So I'm not trying to say that radar is the panacea and it's going to solve everything. I do like these other sensors. I just showed this video. I like this one because the robot is it's sort of moving away from a mock habitat. It's going to do a direction switch as if it was heading off to somewhere else to pick up some cargo. And maybe I'll just speed it along. Oh, it's covered by the zoom controls. I can't speed it along. And then it's going to return, and maybe it's now bringing this cargo back, and it needs to dock back to the habitat where it started. And this is of course, now driving backwards, which is a little bit harder. And we're able to stop. And in this test, we were actually just 1 centimeter away from where we started. So cameras and LiDARs are great. LiDARs are very precise. We can do very nice driving with them. Actually, here's another LiDAR example where we're now not just following routes, but detecting obstacles and trying to make local plans to avoid those obstacles while following the route. So every time we detect an obstacle, we actually run a sample-based motion planner to make a little detour around those obstacles and then get back into our tracks and then keep following the long-range plan. Okay, so I like those sensors, but they're great until they aren't. And anything that's got an optical surface on it starts to get very challenging when you're driving around off-road. So how many people have driven around in a really dusty off-road environment and then ended up with crap all over their optics, and then they had to stop and clean it off, right? Happens all the time. In underground mining, it was a very dusty environment, so we had compressed air that was blowing air against our optical surfaces continuously just to try to keep them clean. But even then, it got challenging. So here are some examples where maybe LiDAR in particular doesn't do so well. And these are not from our work. This is from colleagues around the world. So in the top left, we've got Francois Pomerleau's work where he's actually got a snow gust that came up to his vehicle, and you can actually see the snow gust in the LiDAR data. And he was trying to drive a straight path, and based on that, there's just so much going on in the scene that his odometry failed and he drove off the route. Costas Alexis's lab did a lot of work where they were trying to fly through maybe smoke-filled corridors to mock up a burning building and thinking about a robot that might help firefighters. And they showed the severe attenuation of their LiDAR data in these smoke-filled corridors. And then Martin Magnusson in Sweden and his group, they've been doing a lot of work for underground mining and thinking about what sensors would be applicable in those environments. And actually, here's a vehicle that its job is to pick up dirt, and it generates a lot of dust in the process of doing that. And the LiDAR data, actually, you can see all the dust, and it creates artifacts and makes it really hard to localize. So as I said, cameras and LiDARs are great until they aren't. And radar is something that actually just naturally sees through all of these conditions, just based on the fact that it's using a longer wavelength than the optical spectrum. So maybe we can think about using radar to do autonomy tasks. And as I said, radar, I think, is an undersubscribed sensor in robotics. We recently had this survey paper on radar and robotics. There's been a nice renaissance, I would say, over the last maybe 7 years, where people are coming back to radar. There's a few more interesting units on the market, right? We can access these radars that cars are now putting behind the bumpers in the automotive space. So those are phased array radars, and they have sort of limited field of view. It's actually a little hard to get access to the raw data from those radars because the vendors typically run some kind of clustering algorithm on the raw data, and they only provide you access to those clusters. There are some notable exceptions. I think the Texas Instruments phased array radars let you access the raw data. But the radars I'm going to talk about today are actually different from those. They're actually these spinning radars, and in particular, NavTech. Anyone seen these NavTech imaging radars? Yeah. So this is the kind of data that these radars produce. It's quite rich if you look at the raw data, right? It looks somewhat image-like. You can make out very clearly features like buildings and even cars driving around on the road. And so the question is, could we do as well as we're doing with cameras and LiDAR using a sensor like this for localization? So I'm going to focus primarily on localization in this talk so that we know where we are when we're driving off-road. So in addition to being able to see through all of these interesting weather and particulate matter kind of conditions, radar has a few other interesting properties. So do people know how radars work? Frequency modulated continuous wave? Okay, not so many, so I'll do just a 10-second tutorial or 15-second tutorial on this. So it's a little different than a typical time of flight ranging principle. So normally in like a LiDAR, you send out a pulse of light and you have a clock and you time how long it takes to get back. Based on the speed of light, you work out the range. In frequency modulated continuous wave ranging, you're doing something slightly different. You're sending out a modulated pulse, perhaps with increasing frequency, which corresponds to like a chirp, an up-ramp chirp in the frequency versus time plot. And then what happens is that chirp bounces off the target, it comes back, and due to the time of flight, it gets shifted this way, but you can also think of it as being shifted in the frequency spectrum, right? So if you compare the green to the red, there's sort of a delta F, a shift in the frequency between those two chirps. And so that's indicative of the time of flight, and you can work out the range based on that. Unfortunately, also, another component of the delta F comes from the Doppler effect. So if there's a relative speed between the target and the transmitter, you'll get a second delta F that gets stacked on to the first delta F. And so that can be a little bit tricky. And so one way that you can get around that is you could run an up chirp and then a down chirp and then an up chirp and a down chirp. And if you compare the up and the down chirps, one of those delta Fs switches sign. And so when you look at the two delta Fs from the two chirps, you get two equations and two unknowns, and you can basically then solve for both range and velocity. And so now you've got an extra channel of information, which is this velocity channel. So now you're getting something more than what a typical LiDAR or a camera would produce. In fact, there are now frequency modulated continuous wave LiDARs, which I'm not going to talk about today, but we've been doing a lot of work with those as well. But radar has been the place where this type of ranging has been used for many decades, basically since World War II. And so we've been thinking, I'll start my story just a little bit on the road before we get into off-road. We've been thinking about whether we could replace LiDAR as a primary localization sensor on a car. I took a ride over to Santa Monica in a Waymo while I was here. Very, very robust. It's relying a lot on LiDAR for localization. And the question is, could we do just as well with one of these imaging radars on top of our car? And to that end, we've been building up a big data set called the Boreas data set, which is open source online, hosted on AWS. There's a leaderboard. Data gathered over about a year through all kinds of different lighting and weather conditions. And one thing that we really focused on was we drove the same route over and over again to collect the data. And so you could use one pass through the environment to build a map, and then a subsequent pass to try to localize against that map. And you can mix and match all the different passes to really test out your localization algorithms. So I encourage you to take a look at that. And so we've been using that data to build out our localization algorithms. We could start maybe talking about odometry. So typically, if you're using a LiDAR, you might use something like an iterative closest point cloud matching algorithm to estimate your motion. We've got a Fast Leo 2 author in the audience. Yishi Kai is going to come and be a postdoc in my lab in January. So they did some great work trying to estimate motion from LiDARs, along with many others. And you can do something a little different when you have this extra velocity channel with the radar, right? So one of the challenges with using iterative closest point is you have this expensive step of doing correspondences. You have to find the points in one cloud that match to the points in the other before you can estimate the motion. But now that you've got a velocity channel, you can actually skip the correspondence step altogether and just use the radial velocities from the radar to try to estimate your motion, more like an optical mouse, right? It's computing something more like a flow. Turns out you can only measure the translational velocities with radial velocity measurements, but if you couple that with a gyro, you can now measure all 6 degrees of freedom of velocity, and then you can integrate that over time to estimate your motion. And to do this with radar, it turns out to be pretty tricky because there's a lot of artifacts if you look closely at the radar data. So we have to do some ransack kind of stuff to reject all the outliers from these radial velocity measurements. But if we do that, we can get a pretty clean measurement of our platform velocities, the translational velocities, which are coupled with the gyro, and then we can integrate that for pose over time. So we've been testing this in more and more challenging on-road conditions first. So sort of more benign conditions on the left of this slide, and then more challenging conditions on the right. So the classic degenerate problem for ICP is a long straight tunnel because your point cloud is going to look the same. We can still estimate motion in those degenerate cases because we're getting radial velocity measurements, and so we can do pretty well. And so the results start to look something like this. So in the benign conditions, if you start to compare to something that's doing correspondences and point cloud matching, we do about the same. But when you start to get into these more challenging conditions, you start to see red is ground truth, green is our best Doppler velocity algorithm, and we're sticking pretty close to the ground truth. But the algorithms that are using point correspondences get confused, and so they foreshorten the length of the tunnel or the skyway, for example. The other thing is because we're not doing correspondences, our algorithm runs much, much faster. So we can basically run this algorithm in a couple of milliseconds per scan on a single core, actually. So that starts to look interesting, right? We've already got some resilience to weather and particulate matter. We've got some resilience to geometry being degenerate in the environment just by switching sensors. In fact, we had a paper here at RSS where we were combining both point cloud correspondence. Actually, sorry, we weren't doing that. We were skipping point cloud correspondence altogether. And we were directly matching the raw radar scans to one another, accounting for the Doppler effect, accounting for motion distortion, and we were able to beat basically all of the other Doppler odometry algorithms that are out there. So that's just ego motion estimation. Now we could talk a little bit about localization, right? So we want to go through the environment once, build a map, and now we want to localize against that map. That's basically how the Waymo cars are able to position themselves. So we built point cloud-based localization. So we can't really use the velocities to match back to a map. You need to go back to the point cloud correspondences now. I won't bore you with the details because we're basically doing something like iterative closest point. But the bottom line is that at the moment, we can estimate ourselves to within about 5 centimeters using LiDAR and about 9 centimeters using radar. So we're catching up on the LiDAR. We're just not quite there yet. And I think the reason is the sensor is just a little less precise. The raw data is a little less precise in the radar than in the LiDAR. OK, so now let's switch to off-road. So I've had a long-term love with this problem, which we call visual teach and repeat, which is the idea of maybe you've got a robot that's going to operate in a particular contained environment for a long time, like a mining environment. And what we do is we drive through the environment manually once first. We show the robot all the paths that it's allowed to operate on. And during those demonstrations, we log sensor data and we build up local submaps that we attach along these paths. So we call that the teach pass. And in the repeat pass, we take the live sensor data, we match against these submaps to determine where we are. And then once we know where we are relative to the path, we run a model predictive controller to zero the errors over time. And that actually looks good enough that we can exactly track our path, actually using very basic techniques. So one laptop, one forward-facing stereo camera in this video. There's only one demonstration of every path segment. although we can connect them together into an interconnected network of paths. So there's a 5-kilometer network of paths shown on the left of the slide. In this work, this is almost 10 years ago, I'll stress there's no GPS here, there's no IMU, there's no DNNs because this was pre-deep learning, there's no global map, and we're not exploiting any semantics or structure. And yet that's good enough that we can drive exactly in our tracks. And it turns out that even with cameras, we could start to deal with some lighting, but it gets more complicated. So the thing that we've been thinking about lately is, could we do the same thing using radar? Because then we would be robust immediately to lighting and weather and all these kinds of things. And it turns out we can do that. So we presented the first radar teach and repeat algorithm at ICRA this year. So this is a video basically from that talk. So this is actually right outside my lab. We have this very nice forest literally on our campus that we can drive around on and do some testing. So this robot has already driven the path once, and you can see the long path through the woods. We like to drive in the woods because it's actually really challenging. I'll talk a little bit about why we do that more in a minute. You can see the radar data that we're getting up here on the right. It's not a lot of information. Bushes don't produce a lot of great solid returns for radar. I was actually pretty amazed that this worked in the end. There were quite a few secret sauce tricks that went into getting this to actually function. But in the end, it actually works, and we can drive in our tracks, even in these quite challenging off-road environments. So it's literally localizing off bushes with radar. And you might ask, well, how well does it do that? We did that test. So we've been building up this path following stuff for a long time. So we've got pretty much the state of the art in both camera and LiDAR-based path following. So we compared to our best, which was the LiDAR. And the net of it is that if we use radar, we're getting about, if we use LiDAR, we're getting about maybe 10 centimeters of path tracking error, RMSE, based on a post-processed GPS. And with radar, again, it's similar to what we saw on road. It's about double the path tracking error. So we're getting about 20 centimeters of RMSE error. And there's some reasons for that we can talk about next. We did a lot of testing. Those are all the loops that we did around my campus. And I'll show you some stuff where we actually got out into other test areas as well. So I wanted to maybe think about what's actually challenging here about trying to do this with radar. And maybe you can take a look at these videos. And again, this is a progression from sort of more benign, easy conditions on the left to more challenging conditions on the right. So look at the left. You can see a fence. You can see a tennis court. There's a chain link fence around the tennis court that shows up. There's some buildings. So there's some man-made structure there that's providing very solid returns from the radar, and that actually makes it quite easy to localize. In the middle, we're seeing the conditions that we saw from the video that I just showed of the robot driving around. So this is fairly level terrain, and we're driving through a forest, and you're seeing bushes and trees, but no man-made structure. And that's already starting to get a little challenging. Actually, you can see a fence in the top of the middle one right now. And then on the right, we're seeing a fully off-road forest road that's pitching and rolling. And if you look carefully, you can see as the robot pitches, that'll be indicated by the fact that the radar is getting ground strikes. I should have been more clear that the radar is actually only imaging in 2D, not in 3D. Right? So it's got a cone. It's not as precise as a LiDAR. It's got a cone that's basically spinning in 2D. And so there's a lot more challenges, I think, still ahead. We've been doing testing mainly at my campus so far, but trying to get it to actually work on these more severe three-dimensional terrains, I think, is still an open problem. And to that end, kind of like our on-road data set, I've been collaborating with the University of Laval, a former postdoc of mine, Francois Parmelot, who's a really fantastic field roboticist. He has, part of his university actually owns a giant test forest for ecologists, and he's sort of repurposed it for doing robotics. So it's called the Forêt Montmorency in northern Quebec. And so we've been developing the FOMO dataset, FOMO for Forêt Montmorency, where we've been gathering data over the course of a year through all kinds of different conditions. And if anyone's been to Quebec in the winter, you will realize that there's a lot of snow there. And so it's a really interesting site because the altitude of the road actually changes by about 3 meters just from the fact that there's snow on it compared to when there isn't snow on it. So it's a very challenging test environment. So we've been, mainly Francois' group has been building up this test rig on a Warthog robot, and it's so challenging that you have to put tracks on the robot to be able to drive around in the snow. So we hope to make this data set public fairly soon. We're about a year into the process of logging a whole bunch of data and making that available to everybody. So hopefully this will do what the Boreas data set did, but for off-road. Here's an example of some of the data from that. So you can kind of see the cameras. It looks wildly different once you've got the snow, 2 meters of snow on the road that's been compacted down. There's some LiDAR data, and then the radar is at the bottom. Again, it's only 2D, right, the radar. So the question is, can we keep operating in these environments with only a 2D sensor, or is that not going to be enough? Maybe 3D LiDARs or radars will come along, and that'll make our lives easier. Here's an example of our off-road radar teach and repeat. It's again, we've already taught the route. You can see a map of the route that was constructed during the teach phase on the bottom right, and the robot is now repeating that route. On the level, it's doing just fine. It's a boreal forest, so all the trees are coniferous, so they don't drop their leaves or anything, so it doesn't look so different. But you can see the robot's really struggling here. So as soon as it goes into this sort of pitching and rolling to move up off the plowed road onto the deeper snow, then it actually loses localization there. So the localization was the cause of that sort of swerving as it got up onto the high ground. And then once we're on the more level terrain again, it seems to do fine. So I think there's still some work to be done, but it's interesting to see that it works pretty well in a lot of situations, but there are sort of these corner cases that we need to deal with still. How are we doing on time?
13 minutes or so.
Okay, this talk's going to be shorter. We'll have lots of time for questions. Okay, so the other thing I just wanted to mention is that another place where radar off-road can be really useful, I think, is marine robotics. So Navtech, the manufacturer of the radars that we've been using, they do a lot of work in marine. And so one of the other advantages of radar that we didn't talk about is that it can actually be much longer range. Right? So there's a reason why we use radar in air traffic control and things like that, is that because of the longer wavelength, we can get it to penetrate through things for much further. So this robot here doesn't have a radar on it, but I just want to say there's a lot of interesting off-road challenges in marine robotics. How many people are surface vessel people? One, maybe. So I thought this problem wouldn't be so hard. So for the last few summers, this is actually my cottage lake. So we've been taking this little robot up and trying to do some navigation, and it turns out to be pretty difficult. Things like aquatic plants and all this stuff in the water, actually, it's a much harder perception problem than I was expecting. And even localization is pretty tricky, right? Because you're often not so close to the shore. Then GPS might work fine, but if you don't want to use GPS, then other sensors get tricky. But again, radar could be a solution to that because you can actually see much further. So one thing we've been doing recently is we now have a new boat, which is much nicer than the old boat. The old boat was actually a little small. Once we put all the stuff on it, it was actually almost underwater. But this robot is much bigger, and now we're able to put our radar on it. And this radar has a 1 kilometer range, so we can actually be pretty far from the shore and still detect. So some of the early work we've been doing, you can see in the video on the left, where we've been matching the radar scans to the Google Earth imagery for positioning. And so we can do about as well as a single receiver GPS, just by matching the radar data to the satellite map. So I'm actually already at my conclusions. I guess I didn't time this very well, since when it's pretty rare that a professor ends up finishing early, but here we go. So I think there are some advantages. Maybe I've convinced you that there are some advantages of using radar. We could start with the fact that because of its longer wavelength, it can see through all these different lighting and these weather conditions. As I just said, it's probably longer range, so we can get about 1 kilometer out of these fairly compact sensors. So they're about the size of a coffee can, the smallest ones. And then I think the velocities are also interesting because they can help with these geometric degeneracies. So there's quite a few advantages, but along with the advantages come some challenges, right? So I didn't talk too much about it, but there's a lot of artifacts in the radar data, like very well-known artifacts. But there's 70 years of radar research on how to model those things and start to deal with those things. I didn't talk too much about it, or I didn't talk about it, but we've also been using deep learning to try to clean up the raw radar scans and try to reject some of the artifacts so we can get a cleaner starting point for our algorithms. And that actually does pretty well. So it's able to pick up some of the classic artifacts and reject them. So I think these imaging radars are also a bit challenging because they're scanning in 2D instead of 3D. So maybe there's going to be a 3D one, but mechanically the way they work is they've got a transmitter that hits a 45-degree reflector, and that reflector is actually the thing that's actuated and spins around. And so it might be tricky to get more beams in there because of the mechanical constraints of that reflector. And I just want to say that there are data sets out there. So I already talked about the Boreas data set and the FOMO data set for on-road and off-road. And we're actually going to be logging a pretty extensive marine radar robotics data set this summer, which we'll call the 9 Mile Lake data set, which will be from this robot. And it's going to have LiDARs, radars, stereo camera, post-process GPS. So I think that's all I have. I got to do all the talking. The students and the postdocs did all the work. The sponsors paid for everything, so thanks to them. And I'll just end on this slide and say, as it was mentioned in the intro, I'm taking over as the editor-in-chief of the IEEE Transactions on Field Robotics. I think this community would be a great set of people to send some of their papers into to the journal. We're only about a year old. The long story is the editorial team started as the Journal of Field Robotics. Then we all resigned en masse in protest because the publisher was doing weird things, and we started Field Robotics, and then that was a bit hard to maintain, so then we got acquired by IEEE, and now we're the IEEE Transactions on Field Robotics. So it's only 1 year old, but it's really like 20 years old because the people are the same people, and that's what really matters. So please send your papers, and I'm happy to take any questions.
Radars either on the same robot or on two robots that were operating close by, would they interfere with each other?
That's a good question. We've never tried that. We have two radars on two different robots, but they're usually in quite different environments, so we don't. I haven't tried that. Good question.
So I was wondering if you put two, maybe you could put them at like one at an angle, one.
So people do operate these radars in a push broom fashion, and then you can start to build more three-dimensional models from them. We haven't tried that, but some of our collaborators have done that. But for the crosstalk between them, I'm not sure.
Maybe you could time the beam so that they don't.
Oh, that sounds hard. I think usually in LiDAR, the way that gets handled is you can code the pulses in some way so that you know which pulses come back from your radar. Maybe there's a way to do that in the, LiDAR. Maybe there's a way to do that in the radar as well.
For the doc, I have two questions. One on the Doppler odometry. You mentioned you get Vx and Vy from the radar and then you get gyro.
Yep.
What do you do about the Z translation? Do you have like any constraints that you are on a flat surface or?
Yeah, so we typically, when we're using radar, we're typically just localizing in 2D. So because we're doing this topometric localization, we're always localizing against the current submap. So the notion of a global frame is anathema to us. We don't care about global frames. We're only localizing in local submaps all the time. And so even if those local submaps are pitched and stuff, it doesn't actually matter.
The follow-up would be that the sample that you showed when you were going in the forest and the radar was in blind, for the visual teach and repeat, do you optimize the map before running the route again?
No, again, when we're doing teach and repeat, we eschew global maps. We don't like them. We want to operate only on local maps. So we don't actually ever try to relax the global map into the local maps into a single global frame. That's just not a thing we do. But we are keeping, like if we're using LiDAR, we are actually building a local three-dimensional map all the time. With radar, we just can't do that because the sensor doesn't provide it. Unless you maybe did this push broom thing. There are some people that have been trying to use the fact that the cone, there's a cone of information, and they're trying to like use some kind of neural radiance field style map representation to take that data and turn it into three-dimensional maps, but I'm unconvinced, I would say, that they're actually building a 3D map.
So some fair cool videos are showing the vehicle pitching up and going down these slides and bumps and all. When you're doing this repeat, do you actually account for this geometry, or is it purely reactive?
Like when you saw the vehicle going down the sand slide?
Yeah.
Well, it knows where it is all the time. It doesn't necessarily, we don't necessarily have a good model of the vehicle when it's in a slide, but the algorithm is able to reject disturbances, right? So like if MPC is predicting you're going to be somewhere and you end up somewhere else, that's exactly what feedback is for, in my opinion, right? So feedback kind of solves that problem. Yishi?
I'm just curious, because you only talk about like all LiDAR only and radar only, or camera
Yeah, so there's a couple of answers to that question, which is yes, you could put all the sensors together. If you could afford the processing to process them all, you could probably do better by putting all the sensors together. There's some practical constraints, which is now you've introduced some extrinsic calibration problems, some extra compute problems. And it turns out now you're writing systems papers instead of algorithm papers, and no one will cite your papers because no one can reproduce your setup. So we try to stick to one sensor because then it's easier for other people to kind of, you're sort of being a little more methodical and trying to say like, how well can this do and how well can this do? But yeah, if you're going to build a real system, you might take the best of all these things and put them together. But no one cites those papers.
Can you speak to like the swap requirements of the radar compared to like the radar?
The swap requirements.
Yeah.
I'm not sure what you mean.
Oh, like size, weight, and power.
Ah. Yeah, so I mean, cameras are going to win on that every time, right? Because they don't have to carry their own power source, basically, right? They're using passive illumination. I would say radar is still the heaviest, right? So the smallest LiDARs are sort of grapefruit-sized, and the radars are about this big, and the main constraint is actually the reflector. So because of the physics of the way the ranging is happening, it's really hard to make at least these kind of radars, it's hard to make that reflector really small. The phased array radars, the ones that sit behind the bumper of an automotive vehicle, those are pretty small. And actually, there's a reason why they use those, mainly because they can see through particulate matter. But power is probably about the same once you start talking about phased array, because it's solid state, right? But the mechanically actuated radars, yeah, they're not fantastic on power. Am I done?
I think we've got time for one more question. We've got 2 online
Okay.
questions.
Yeah, maybe you need to moderate those for me. Oh, maybe I can see them here. Yep.
I can repeat it. You talked about integration with gyro. Can you elaborate how important this integration is and what happens when you only use radar?
Yeah, good question. So when we were doing the radar teach and repeat, it turned out that we really did need to use the gyro. So the radar-only odometry was not good enough for us to maintain a stable system that was able to drive off-road. So integration of the gyro was actually critical to that. And we did the ablation, and we just showed that it wasn't even robust enough to report in the paper. So I think you definitely want to use a gyro. And why wouldn't you use a gyro? A gyro is super cheap, and it really just sort of limits the drift in heading very, very easily. Even a low-cost one.
All right, last question.
Yep.
Have you considered like you use a weight radar?
This is millimeter wave radar. Yeah. Yeah. So automotive radars and these imaging radars, they're all sort of in the 77 gigahertz spectrum. So this is millimeter wave. Yep. All done? All right. Thanks, guys. Oh, yeah. Sorry. You mean I can't take it with me?